Today we're going to discuss least upper bounds. Let's review from last time. Say that we have a field. That is, we have a triple consisting of a set F, addition plus, and multiplication dot. Given a subset P of this set F, we may define an order relation by saying x is less than y whenever the difference y minus x is an element of P. We'll say that now a quadruple consisting of F, addition plus, multiplication dot, and our order relation P is an ordered field if the following three properties hold. First, we require the trichotomy property. That says that for every element x in our set F, either x is 0, x is positive, or x is negative. That is, either x is 0, or x is in P, or negative x is an element of P. Next, we'll say that given two positive elements, their sum is positive. That is, whenever x and y are elements of P, the sum x plus y is an element of P. And third, the product of two positive elements should be positive. That is, whenever x and y are elements of P, the product x times y is an element of P. As a remark, both the rational numbers and the real numbers are examples of ordered fields where our set P just consists of those positive elements, that is, those elements that are greater than 0. On the other hand, the complex numbers does not form an ordered field. We'll come back and discuss this example later. Using the trichotomy law, we can define an absolute value as follows. Given an element x of our set F, either the absolute value is 0 whenever x itself is 0, the absolute value is x whenever x is positive, and the absolute value is negative x whenever x is negative. Using this, we then have a few properties that we'll put together and call the triangle inequality. First, we see that the absolute value of x is greater than or equal to 0 for any x in our set F. Moreover, the absolute value of x is 0 if and only if x itself is 0. Next, given two elements a and b, the absolute value of their product is the product of their absolute values. That means the absolute value of a times b is the absolute value of a times the absolute value of b. Third, the absolute value of the sum is greater than or equal to the sum of the absolute values. That means the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Moreover, we have a strict inequality if and only if a and b have different signs. That is, the product of a times b is negative. Using all of this, we can now define the concept of a least upper bound and a greatest lower bound. Let's say that we have an ordered field, and let a and b be subsets of our set F. We'll say that an element b is an upper bound for capital A if b is greater than or equal to x for all x in capital A. Similarly, we'll say that an element b is a lower bound for capital B if b is less than or equal to x for all x in capital B. An element S is said to be a least upper bound for capital A if two things hold. One, S is an upper bound for capital A, and S is less than or equal to B for all upper bounds, lowercase b, for capital A. In this case, we'll denote S as sup A and call this the supremum. Similarly, an element S is called a greatest lower bound for capital B if two things hold. One, S is a lower bound for capital B, and two, S is greater than or equal to B for all other lower bounds, lowercase b, for capital B. We'll let this S be I and F of B and call this the infimum of B. Notice that if B looked like the negatives of all the elements from A, then the supremum of B is just the negative of the supremum coming from A. Finally, we'll say that an ordered field is complete if it satisfies the following property. We'll call this the least upper bound property. Every non-empty subset A of F that has an upper bound has a least upper bound. Similarly, the greatest lower bound property states every non-empty subset B of F, which has a lower bound, has a greatest lower bound. Let's try to discuss some examples of this. First, let F be the collection of rational numbers, and let's consider that non-empty subset A, which consists of rational numbers less than 3. An upper bound for this set A is the number 4 because every element from the set is less than 4. Actually, another upper bound is S equals 3 because every element in this set is less than 3. There are lots of upper bounds, but we'll see that S equals to 3 is the least such upper bound. More generally, given a rational number R, we can consider the set A of those rational numbers that are less than R. In this case, you can show that the supremum of this set is just the rational number R. Let's consider a slightly more complicated example. Again, let F be the collection of rational numbers, and let's consider the following non-empty subset A. It consists of rational numbers Q that are either negative or satisfy the condition x squared is less than 2. An upper bound for this set is B0 is equal to 2 because every number x in the set satisfies x less than 2. Moreover, another upper bound is B sub 1 equals 3 halves because every element x in the set has to be less than the square root of 2, which is equal to 1.414. In fact, there are infinitely many upper bounds, B sub 0, B sub 1, B sub 2, and so on, which actually we can choose to get closer and closer to the square root of 2. There's a recursive formula that you'll see on your screen that explains how we might construct such a sequence. Here we'll plug in very specific values so you can see how these numbers do get closer and closer to the square root of 2. Actually, this shows that this set A has no least upper bound S that's a rational number because, given such a rational number S, we can always choose our B sub n's that lie between this upper bound S and the square root of 2. That is, the B sub n's really do get as close to the square root of 2 as we'd like them to be. We're tempted to say that the supremum of this set A is the square root of 2, but the square root of 2 is irrational, so we can't do this. This means that we've constructed a set A that has an upper bound, but it has no least upper bound. In fact, using this, we see that the collection of rational numbers is not a complete field. Indeed, we've constructed a non-empty subset A, which has an upper bound, but it has no least upper bound, showing that the completeness axiom, fails. Eventually, we're going to prove that the real numbers and the complex numbers are indeed complete fields, but this will take some time to show. We'll give a general property here that allows us to better understand what the least upper bound and greatest lower bounds of a set really are. Again, let's say that we have a complete ordered field, and let's let A and B be non-empty subsets. Let's assume first that A has an upper bound. For each epsilon in F, satisfying epsilon greater than 0, there exists an element A sub epsilon coming from the set A such that A epsilon plus epsilon is greater than the supremum of A. What this actually means is we can always choose A sub epsilon in the set A to get as close as we'd like to the supremum of A. So while the supremum of A is actually not an element in the set A, it does say that we can get as close as we'd like to get to this supremum. Similarly, let's say that capital B has a lower bound. Then for each epsilon in F, satisfying epsilon is positive, there exists an element B sub epsilon in the set capital B such that B sub epsilon minus epsilon is less than the infimum of B. Just like before, the infimum of B need not be an element of the set B, but we can always find an element B sub epsilon in this set that gets as close as we'd like it to get to this greatest lower bound inf of B. We'll sketch over the proof of these two statements. First, let's try to show the first one. Let's assume, by way of contradiction, that for any epsilon, we have the element a plus epsilon is less than the supremum of the set A for all A in the set A. If you actually work this out, then what you'll see is that the supremum of A minus epsilon is an upper bound for A, and this will contradict the fact that we assume that sup A is the least such upper bound. Let's try to prove the second statement. Let's assume, by way of contradiction, that for any epsilon, we have B minus epsilon is greater than the infimum of the set B for all B in the set B. Then this means that B is greater than the infimum of the set B plus epsilon for all elements B in the set B, showing that inf of the set B plus epsilon is a lower bound for B. But this contradicts the assumption that inf B is the greatest such lower bound. We'll use all of this to introduce one last concept that we'll discuss quite a bit in the next coming lectures. Again, say that we have an ordered field, and let's let A be a subset of F. We've already seen that an element is a lower bound for the set A if A is less than or equal to X for all X in the set A. Similarly, we'll say that an element B is an upper bound for the set A if X is less than or equal to B for all X in the set A. We'll say that our set A is bounded if it has both an upper bound and a lower bound. Say that we have a sequence of elements x0, x1, x2, so on and so forth from the field F. We'll say that this is a bounded sequence if, once we place these elements into a set capital A, this is a bounded set. A set A is bounded if and only if we can find a number m greater than or equal to 0 such that the absolute value of x is less than or equal to m for all x in A. This goes over the usual definition that we think of when we say that something is bounded. Let's assume first that there does exist an m such that the absolute value of x is less than or equal to m for all x in the set A. Well, we have two cases to consider. If x is positive, then we can say x is less than or equal to m because the absolute value of x equals x. And putting all of this together, we'll see that negative m is less than or equal to x is less than or equal to m. We find a similar statement when x is negative. This means that we can think of lowercase a as negative m as a lower bound, and b equals positive m as an upper bound for this set A. This shows that our set A is indeed bounded. Conversely, let's assume that our set A is bounded. We'll need to try to construct this bound capital M. Well, to say that capital A is bounded means that there exists elements A and B such that A less than or equal to X less than or equal to B for all X in the set A. Recall that B is less than or equal to the absolute value of B. So putting this together, we'll see that negative of the absolute value of A is less than or equal to X is less than or equal to B. Similarly, negative the absolute value of B is less than or equal to negative X is less than or equal to A. So let's choose capital M to be the larger of the absolute value of A and the absolute value of B. Then we'll find that the absolute value of X is less than or equal to M for all X in the set A. Thanks for listening.